In this section, we are going to take everything we've learned from 9.1 and 9.2, which was substitution and integration by parts, and all of those we did those processes with indefinite integrals. So remember what an indefinite integral gives us. An indefinite integral gives us a function. And today what we're going to see is, well, how do I still use this process of substitution and elimination in a function or in a definite integral? And remember what a definite integral gives us. A definite integral gives us a number. So there are a couple ways that you can do this. I'm going to do, you can always find, I'm just going to show you some examples actually, because you've read the book, right? So you can always find, well, let me write this down. Let me finish writing and then I will talk. That's a good idea. When I'm evaluating something like this, so remember when we take the integral from a to b of some function, how do we evaluate this? We take an antiderivative of f of x, of little f of x, and I evaluate it from a to b. So one of the options, so there is one option, and I'm not going to do it this way because it takes longer, is to just evaluate the indefinite integral. You're going to evaluate this guy, which is, I know you already see that we're going to use substitution to do this. You're going to evaluate this guy, and then you're going to plug in bounds afterward. So plug in bounds later, okay? I'm going to do it a little bit differently, so we'll be able to see that you can do this just a little bit differently, where we don't actually have to do two steps. We can actually plug in the bounds at the same time that we're evaluating the integral. But I'm going to tell you right now, you got to do this how I do this. I'm going to be very, very picky about notation. You are in Calculus 2, Business Calc 2. You should be writing mathematics well by now. So I need you to make sure that when you do this notation, you do the notation how I show you. So if I look at this integrand here, if I want to evaluate this, this is substitution, right? I'm going to let u equal x cubed plus 1. I need to see this, people. I need to see you choose your u. I need to see you solve, for what you want to get rid of. I need to see your work. Okay, if you don't show me your work, I'm not going to give you any partial credit if you get something wrong. You actually won't get credit for the whole problem. Well, full credit for the problem because you need to show me your work. Okay, so this is great. So this equals, I know I'm off by a third, so I have 1/3. And then I know this guy right here is replaced with u. So I have u to the 1/2, and then here I have du. So that's lovely, and everybody's happy. Because we're able to take the antiderivative of that. Here's the thing. There's always something, right? These bounds right here. So 2 and 0. These bounds apply to the variable, excuse me, x. It's dx. We're deriving with respect to x. So I cannot, listen, I cannot write 0 to 2 here. I don't care if you're even going to bring x back in. I cannot write 0 to 2 here. This right here is wrong because these bounds do not apply to u, they apply to x. So what we must do here is we must just change the bounds. So if we're doing something like u substitution, what we can do is we can look at, well, I have this relationship between x and u. When x is 0, what is u? u is 0 cubed, which is 0 plus 1. u is 1. So where x was 0, I'm going to put a 1. Then I come up here and I look at when x is 2. I want to see this again. You should be doing your work just like I'm doing this on the video. When x is 2, I have 2 cubed, which is 8, plus 1, which is 9. So u is 9. So look at now, I have my bounds going from 1 to 9. Of 1/3 u to the 1/2 du. The great thing about doing it this way is we don't have to come back to x's. Okay, we have redone our bounds. We've redone our limits of integration so that they now apply to u. Right? I have a relationship between u and x. That relationship now has been used to redo my bounds. And now whoa, sorry about that. I just opened the internet for some reason. So now I take the antiderivative, so I have 1/3 u to the 1/2, that's going to be 2/3 u to the 3/2, and I'm going to evaluate this guy from 1 to 9. Okay, so again, because I changed my bounds, I don't have to bring my x back in. So when you do these definite integrals with u substitution, this x cubed plus 1 does not come back in, because again, what does a definite integral give us? A definite integral gives us a number, not a function. So it doesn't matter how I get to that number, right? It doesn't matter how I get to that number, as long as I do it correctly. But if I, that's true, I suppose. But if I change the bounds, that's fine. And then I just, this is 2/9. I plug the 9 in, I plug the 1 in, and I kind of factor that 2/9 out. So I have 2/9 times, well, the square root of 9 is 3. 3 cubed, right, is 27. Minus 1 is 26. So it looks like our answer is 52/9, and we're done. Isn't that great? I love it. Now again, the other way you could have done this, but you're going to have to be careful with your notation, is you actually could have said, well, I'm just going to find the antiderivative here. When you find that antiderivative, you're going to see it's 2/9 x cubed plus 1 to the 3/2. I'm not going to put a plus c because I know I'm evaluating a definite integral. Then you need to start a new line. You need to start a new line, and you go from 0 to 2. You rewrite what you're doing now. Oh, I'm kind of squishing this in. And you say, okay, that's 2/9 x cubed plus 1 to the 3/2, evaluated from 0 to 2. And now you can show me that. But I really just recommend changing your bounds. We know the relationship between u and x, so it shouldn't be too hard to do that. I hope that makes sense. Let's maybe do one more. Oh, let me just get a new layer. All right, so another example, what if we had something like x over e to the x squared dx from 0 to 1. So I'm going to rewrite this really quick. So this will be 0 to 1, x e to the negative x squared dx. I know I'm going to do u substitution, so u is going to be a negative x squared. Oh, sorry about that. du, I have a meeting, equals a negative 2x dx, but this is way more fun. I would much rather do calculus with you than go to a meeting. Okay, so look at what I have. I have the integral of, I'm off by a negative 1/2, right? So let's give ourselves some room here. So I'm off by a negative 1/2. I can just bring that out front. I get e to the u du, and I am not going to put 0 to 1. When x is 0, what is u? 0 squared, which is 0. That's great. When x is 1, what is u? Well, it's 1 squared, which is 1. I want to point out really quick, this is an easy mistake to make. That negative is not being squared. It's not in parentheses, so this is just negative 1. So we're actually going to go from 0 to negative 1. I know that's a little bit strange. And actually, when I would do this, see that's negative right here? Remember, if we switch the limits of integration, take their opposite, the opposite order, that just changes the sign of the integral. So I would just switch our order. I think you know this by now. I have some issues with notation and how things should be. So I'm going to do negative 1 to 0. It bothered with me that 0 is first, but it doesn't matter. This actually doesn't matter because you'll get the same thing. And again, I don't come back to x's because I've changed my bounds. So I have e to the 0 minus e to the negative 1. So what do we have here? Well, this is 1. This is, I can't really do much with. So we could just write this as 1/2 times 1. You could write that as maybe 1 over e if you wanted to, or you could just leave it as e to the negative 1. That would be fine as well. All right, I hope that makes sense. Let's, that's, with this section, that's the big one, is this idea of substitution and changing the limits. And there's, like a box in the book that you should copy and all that good stuff. So let's look at parts then. Parts is really, in parts, you don't really need to, I'm going to do kind of the same example here, But notice that I can't do substitution with this, right? Because I can't let u be x. If I let u be x, then I can't get rid of this x right here. So I get to do parts. I want to say I'm forced to do parts. I have the opportunity to do parts. All right, so really when you're doing parts, you're not actually going to change the limits of integration. Because remember with parts, even though I have this u dv equals the integral of excuse me, Sunny Voodoo, uv minus the integral of v du. Even though I have this, remember, I don't actually rewrite this guy with u's and v's. This just helps me kind of see the process of how to do that. So I'm going to let u equal x. That leaves dv, again, you need to write this correctly, equals e to the x dx. So du equals dx. That leaves me with v equaling e to the x. So remember, I'm just doing this to remember the order of how to do that. It's just a way to kind of remember this. Now, this is a definite integral, so here's where we have to be a little bit careful. When I take u times v, this is x e to the x minus the integral of v du, which is e to the x dx. This is a definite integral. Remember what a definite integral gives us. It gives us a number. It doesn't give us a function, it gives us a number. So if I were to go through and finish this, whoa, I don't know what just happened there. If I were to go through and finish this, I would find what the antiderivative is. I'd finish this up right here. And then what would I do? I would plug in 1 and I would plug in 0 into the entire thing. Well, I can also think of that as plugging in 0 and 1 into this part right here, which has been taken care of. I don't have any other integration to do with this. And then this guy right here, I need to go from 0 to 1. Let me tell you something. I will take off on homework and on an exam if you don't put that 0 to 1 right there. Because I know to you might be like, oh my goodness, Sarah, you are so picky. This is ridiculous. I know none of you talk like that, but if you don't put that 0 to 1 here, this equality right here is completely wrong. This thing right here equals a constant, right? If you don't say this is being evaluated from 0 to 1, then this right here is a function, and it doesn't equal a function, it equals a constant. Okay, so I'm going to be picky about that. So do what I say. That's what you should do. So right here, I'm going to go ahead and plug in 1 and 0. So that's pretty easy. I just get e minus 0. Okay. Over here, I still have to take the antiderivative, which is just e to the x evaluated from 0 to 1. So I get e minus, put parentheses because I have this negative right here, e minus and e to the 0. Don't forget to put in 0 when you evaluate e to the 0 because it doesn't go to 0, it goes to 1. And then if I take that negative through, I get minus e plus 1. And this one is just lovely because everything cancels out. And I just get a 1 there. Okay, I want to do one more example with parts. Again, just to show you notation. That's all that's really different with parts is the notation. So what if we go from 1 to 4, natural log of x over the square root of x dx. I'm going to rewrite this a little bit. 1 to 4, x to the negative 1/2. Natural log of x dx. Okay, remember when natural log's involved, I need my u to be natural log. I can't let dv be natural log because I don't know the antiderivative of natural log, right? And whatever we let dv be is what we are going to be taking the antiderivative of. So I know I'm going kind of fast through this, pause the video if you want to and verify this for yourself, but I let u equal natural log of x. I know I need du because I need uv minus the integral of v du. Okay, so let's see what this equals. So u times v, that's 2x to the 1/2. I like to have my natural log second. Natural log of x evaluated from 1 to 4 because it's a definite integral, minus v, so there's my v, du. I'm going to go ahead and bring that 2 out because I can. And then I have my v, and my du is 1 over x dx. Oh, I'm running out of room. All right, so let's start. Oh, I'm going to need some more room here. Not quite estimate this correctly. So do that. All right, let's put in 4. So remember, this is the square root. So the square root, that's going to be the square root of 4, natural log of 4 minus 2 times the square root of 1, which is 1. Natural log of 1, what's great there is that goes to 0. Here, don't forget, you know algebra. This is x to the 1. 1/2 minus 1 is a negative 1/2. You know, when you do these, well, we talked about that in the last video, but when you do these parts with natural logs, we start seeing stuff that we've already seen. Here, this guy goes to 0. Natural log of 1 is 0. And then this is just 4 natural log of 4. You can just leave it like that. Or if that bothers you, you know, feel free to get a decimal approximation. And then here I'm just taking the antiderivative. And again, you know, the actual calculus on this is pretty easy. It's going to be just, you know, remembering to plug things in. So here I get, again, this -4 I just kind of put on the outside because it's going to go to each term. So I'm not going to really worry about it too much. And what is my final answer? 4 natural log of 4. This is 2 minus 1. That's lovely, which is just 1. So I get 4. Oh, I kind of want to factor that into the natural log. 4 times the natural log of 4 minus 1, but you wouldn't have to do that. It just looks so pretty doing that. Okay, I hope that makes sense. It's one of my shorter videos, which is unusual for me. Again, I'm going to be a big stickler about notation. If you don't do it the way I do it, I'm taking off, and I guess that's your right to get points taken off. But again, you're in calculus 2. You should be able to write mathematics well at this point in your math career. As always, let me know if you have any questions.